Okie dokes. So for today, in the chat, I want you to write down everything you know about the Big Bang Theory. And I do not mean the TV show. That seems to be a common request. Are you talking about the TV show? And unfortunately, I am not talking about the TV show. Um, I have watched the first 4 seasons of the show, I think, 4 or 5, and it gets very bad after that. So I honestly can't even really recommend the show itself. But sure, if you want to talk about the show, you can. Um, okay, but in the chat, I want you to write down everything you know about the scientific theory known as the Big Bang Theory. If you've never heard about the Big Bang Theory before, you can also write down whatever you know about the origins of the universe. Where do you think the universe came from? How do you think it started? How old do you think it is? Write down whatever you know about the origins of the Big Bang Theory. There is a graphic organizer that you can fill out as you go through it. That's the wrong one. So write down whatever you know about the Big Bang Theory. Or whatever you know about how the universe started. How old do you think it is? Where do you think it came from? Did the chicken come first or did the egg come first? These are all very important questions to discuss. Um, you can't see the whiteboard thingy. Ah, that would be helpful. Ah, yes, having the screen would be helpful. Good, thank you for letting, good, it's good now. Yes, thank you for letting me know. So in the chat, write down whatever you know about the Big Bang Theory, and I do not mean the show, I mean the scientific theory known as the Big Bang Theory. How do you think the origin of the universe, what the origin of the universe is? Where did it come from? How did it start? Nothing. Really? That's interesting. Interesting. That's really interesting. Someone else in my fourth period told me that they never heard anything about it, and I think that's really interesting. I could have. I feel like it should be covered in like in, that's really interesting. Interesting. Um, honestly, I can't really. No, I know, no, I know. That makes sense. That makes sense. I don't know when I first learned about it. Yeah, honestly, I don't really know. I feel like it was. I definitely didn't learn about it in high school, and I maybe in middle school, maybe elementary school. I honestly don't really remember, or maybe I just spent too much time on Wikipedia. I definitely do that for sure. Kaboom! Boom! Kaboom! Okay, let's take another couple minutes. What do you know about the Big Bang Theory? Um, how do you think the universe started? Where did it come from? Did the chicken come first or did the egg? Do we live in a multiverse? Are there aliens out there? Are we truly alive? Do we live in a simulation? These are all the questions of the questions to ponder as we talk about today. Okay, so um, scientists believe it started the universe, and they believe that all of the energy and matter was in one tiny speck, and then that exploded and created the universe. Um, And I believe that it's 8.8 billion years ago, the universe began forming by the Big Bang Theory. That is pretty much what we'll be talking about today, is how the universe started and what the Big Bang actually is. So for today, the slides and a graphic organizer are both on Canvas. I did link the graphic organizer a few minutes ago. So you can open it up and make a copy of it. And then that's what we will be talking about today, the Big Bang. So what is the Big Bang? The Big Bang is how we believe that the universe originated. So basically about 13.8 billion years ago, the universe started as a single point. This is what we call a singularity. So I basically want you to imagine every single thing in the universe. So every single car, every single person, every single planet, every single sun, every single star, every single galaxy, and you condense it all into this infinitely small point that is smaller than even an atom. So everything in the universe got condensed into one tiny point 13.8 billion years ago. We don't know anything that actually happened before the universe originated, and I don't think there's ever really going to be a way to figure that out based on our current laws of physics. So, but we do know, however, we do have a very strong idea of what happened 13.8 billion years ago, and that is everything sort of got condensed into one single point. Now, this point was infinitely dense because it was basically infinitely small, and it was extremely hot. Extremely hot. So now I want you to imagine what happens if you are in a room. Like imagine if 100 people were sitting in your room right now. That would be a lot of warmth. It'd be very warm. Well, now imagine if all of that got condensed into an area smaller than an atom. So things would be very hot. Now, a common misnomer is that the universe sort of exploded. There was a giant explosion. That's kind of what it's like, but it's actually more accurately called inflation. An explosion sort of insinuates that there was some sort of chemical reaction, and then it just created this boom, and all this material came out. What it's more accurately called inflation. So instead of the universe exploding and just ejecting all this material outwards, what actually sort of happened was that imagine if you had a really small balloon, and then you inflated it, and then that balloon got bigger and bigger. So that's sort of what the universe actually sort of did. Was it originally started off as a very small balloon, and then you inflated it, and it got bigger and bigger very quickly. And so this process is what we call inflation, just like how when you inflate a balloon, the balloon gets bigger. When the universe was inflating, it was also getting bigger. So as the universe gets bigger, it also means that the universe is going to get cooler. Now, it doesn't mean the universe is going to be cool. It just means that the universe is going to get cooler. So if you gave all these people that were packed tightly together, and you increase the size of the room, these people can all spread out, and now the room's going to be a lot cooler. Same idea here. As the universe gets bigger and bigger, there's more space for all this stuff to move around, and so the temperature of the universe is going to get cooler. So as the universe gets bigger and bigger, it's going to get cooler and cooler, and this is what we call inflation. Now, we do know that the universe is expanding. We have scientific evidence to prove so. And the main scientific evidence that we have that suggests that our universe is expanding is something called redshift. So a huge part of this is going to be learning about how the universe originated, but also what the evidence we have that supports this. Because this isn't just like some theory that someone just randomly came up with. There's a lot of scientific evidence that supports it. The theory itself also makes a lot of predictions that are testable and we can verify. So it's less of a theory and more of a strongly created and proven explanation. So it's less of a theory and more of a good explanation. I think sometimes a theory is a misnomer. It sort of suggests that it's like nothing more than a guess. It's actually more of an explanation. And there's a lot of scientific backing behind it. And it also makes a lot of predictions that we have verified. There's a large amount of accuracy with this. So what is redshift? Because redshift is one of the most important ways that we have verified the fact that the universe is expanding. The redshift is a kind of a complicated thing. You definitely will need to know this. 100%, very important. So what is redshift? So what redshift is redshift relates to light. Light has, if you know, is on the electromagnetic spectrum, which basically means that there's many different forms of light. Each one of these forms of light has a different wavelength and a different frequency. So some of the ways, so in terms of what the different types of light we have, there are radio waves, microwaves, infrared rays, visible light, which is the one we can see, UV light, X-rays, and gamma rays. So microwaves are stuff that you see in your microwave, very low energy. Radio waves are from radios. Infrared is usually comes from heat, and that's what if you know what night vision goggles are, those use infrared light to see. Visible light, that's the light that our eyes can perceive. UV light is the light that's generated from the sun, and it can damage your skin because it's fairly high energy. X-rays is even more higher energy than that, and that's what you use if your bones are broken. And then Chernobyl has gamma rays. If you've watched the show Chernobyl, gamma rays are very dangerous, and they will definitely mess up your body in very disgusting ways. So there are different forms of light. Each one of these different forms of light has a different energy associated with them. That amount of energy relates to two things: the frequency of the light and the wavelength of the light. So light is essentially a wave. What that means is it's sort of like if you were in an ocean, you can sort of imagine the light hitting you every time a wave is hitting you. So, and how long the waves are correlates to how quickly it hits you. So the faster and faster the waves hit you, what's what we call a higher frequency. So frequency is sort of how rapidly are these waves hitting you. And you can think of it as how rapidly the light is hitting you. Right? It's hit bam, 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 bam. So the speed of light is the same, but it's more of like how rapidly are these waves hitting you. And the more rapidly they're hitting you, the more energy they have. So stuff like X-rays and gamma rays, they have very short wavelengths, which means that it takes very little time for the waves to just keep hitting you. So these are going to be very high energy. Whereas stuff like radio waves and microwaves, they have much longer wavelengths, which means that it takes much more time for the wavelengths of light to hit you between waves, and which means it has lower frequency, which is why microwaves and radio waves are not very dangerous. They're not dangerous. They're very low energy. Now, what the term redshift is it means that we are essentially reducing the radiation, the amount of energy that light or radiation has. Radiation is another way of saying light. It's reducing the amount of energy that particular form of radiation has. So basically, the idea is if something originated as an X-ray, but when it came to us as a microwave, that thing was redshifted because the amount of energy it used to have was a lot more than what it has now. It lost a lot of energy in the process. It's called shift because the amount of energy the light has was shifted, but it's called redshift because on the scale of visible light, blue light has a lot of energy and red light has a much lower energy. So redshifting means you're sort of moving towards the side of low energy. There's also a term called blue shifting, and that means when your light is moving towards high energy, your light is becoming more energetic. But we will be mostly talking about redshift. So redshift is a vocab term that you will definitely need to know, for sure, very important. It relates to the fact that redshift relates to the fact that that light has lost its energy lost a lot of energy from when it was emitted to when it hits you. Now, the thing is, on its own, light won't lose its energy. There's no reason why light would lose its energy on its own. Things need to happen in order for light to lose its energy. The most common source of redshift is called the Doppler effect. This basically relates to the motion of the object. So if a source of light, like the star, is moving away from us, the amount of light that reaches the Earth is going to has less and less and less energy. And that's why it's redshifted. Why is this the case? Well, if you think about it, a star that is moving away from the Earth, the light waves are going to take more and more and more time to hit us, which is essentially reducing the frequency of the light, which also means that the wavelengths of light are going to be increased as well. So because the light is taking more and more and more time to hit us, because the frequency between these waves is going to get longer and longer and longer, the wavelengths are going to increase, which means that the amount of energy that light is going to have is going to be decreased as well. And this is actually how radar detectors work in a car. They actually use the Doppler effect to track how quickly your car is moving. When your car is moving towards the radar detector, it's going to compress these light waves together. When your car is moving away from the radar detector, the light waves are going to be expanded apart, and then that's going to be redshifted. And the amount of redshift that the light waves from the car is coming to the radar detector will tell you how fast the car is moving. So same idea here. If your star is moving away from Earth, light is going to take more and more time to reach the Earth, which is essentially going to increase the wavelength of the light, which is going to reduce the amount of energy it has. So the motion of the source of light can create redshift, and this is what we call the Doppler effect. So just like how we can redshift something, we can also blue shift light. And that's sort of the opposite. Instead of an object moving away from you, this time the object will be moving towards you. And so it's going to compress the light waves, and it's going to take less and less and less time to reach you, which means the wavelengths are going to get reduced smaller and smaller and smaller and smaller, which is essentially going to be the frequency of the light hitting you is going to be a lot higher. Because the frequency of the light is hitting you a lot higher, the energy is going to be increased of the light. So the energy of the light is directly related to the frequency. The higher the frequency, the higher the energy of the light. So when you are increasing the frequency of the light by moving towards you, you're going to be increasing the energy. And vice versa, if you are moving away from the source of light, a source of light is moving away from you, the frequency of the light is going to decrease, and then that's going to reduce the energy of it. And that's called the redshift. So redshift, less energy; blue shift, more energy. Now, the reason why redshift is really important is because redshift is one of the main sources of evidence that supports the Big Bang theory, and the reason why is because the redshift itself suggests that the universe is expanding. So basically, what happened was we sort of measured the composition of elements in other galaxies, and we determined what the light spectrum, so what kind of light we should expect to see from the galaxies. When we actually measured the light we got, we realized that the light we got was redshifted by a large amount, meaning that in order for that to happen, these galaxies would have had to have been moving away from us. And the way you could do that is that the universe was expanding. So how would the expansion of the universe create redshift? So the way that this does it is that if the universe is expanding, you're sort of stretching out the wavelengths of light, and you are increasing its wavelength, and thus you're making it lose energy. So basically, by expanding the universe, you're expanding the size of the balloon. So all these light waves that were in the universe are getting stretched out. So to give you an idea of what that means to sort of stretch out the light, I'm going to sort of show you give you an example of it. So what I have here is a slinky. And so basically, I want you to imagine that each coil in this slinky is like a different wave of light, right? So right now, all this coil, the coils in the slinky are pretty, the wavelengths are pretty small. Now, the universe is expanding, it's literally stretching out the slinky. And so the amount of distance between these coils is going to increase and increase and increase. So as the amount of increase, the distance between these coils is increasing, the wavelength, in other words, the distance between the coils, is going to increase as well, which is going to make the energy contained within the wavelengths of light increase as well. So I want you to imagine essentially that a slinky is being pulled and pulled and pulled apart, which is going to increase the wavelength of the slinky, of the light. To give you a more another visual example. So this is what light is. This is what a light wave sort of look like. It'll look literally like this, like a wave. So this is a light wave, and it really just looks like a bunch of ocean waves. The distance between one peak to another peak, this is what we call a wavelength. And so light waves with longer wavelengths are going to be stuff like microwaves and radio waves. They're going to be lower energy. Stuff with shorter wavelengths are going to have higher energy. The reason why is that the longer the wavelength, the higher the frequency. The frequency is basically, if I was sitting here, the frequency is basically how long it takes, the time it takes between this light wave to hit you and this light wave to hit you. It's basically like how specifically are you feeling these waves of light. So if you have a long wavelength, there's the amount of time between waves is going to increase. So basically, if you were a person here, right? If you, let's say you were sitting in, you're like floating in the ocean, these light waves are ocean waves. The frequency would be basically how quickly are these ocean waves hitting you. And the faster these ocean waves are hitting you, the more energy they're going to have. In other words, and additionally, the longer the wavelength, the more time it takes between waves, which means the frequency is lower, which means that the energy is also going to be lower. So what happens if the universe is expanding? So when the universe is expanding, you're really going to take this wave and then we are going to stretch it out. So with this wave, instead of looking like this, and now it might look like this. So we literally took this wave and we literally stretched out all these individual wavelengths. So now, as you can tell here, the wavelength here is going to be very, very big. But if you're standing here and you're feeling sort of how rapidly these waves are coming by, the amount of time between each wave is going to be fairly long. The frequency of these waves is going to be fairly short. So because it takes a long time for you between these waves, the energy of this wave is going to be low. And this is what we call a redshift. Redshift is basically when a light wave goes from being the wavelength of the light gets stretched out. And so what ends up happening is the light has a lot less energy. So redshift light has a lot less energy. And when the universe is expanding, it creates redshift in the light. And so what happened was we observed a bunch of galaxies and we compared what we expected the light to be to what it actually was. And we realized that all of the light we expected it to be was actually redshifted, which meant that the galaxies had to have been going farther away from us, sort of implied that the universe was expanding. There's also something we call blue shift, which I think I mentioned before. For this, we're not going to be concerned about blue shift as much, but blue shift is the opposite of this. So instead of looking like big, all these waves are going to be really. So this is what blue shifted light might look like. So blue shifted light would have more energy, whereas red shifted light has less energy. So the fact that all the light from these galaxies are redshifted is a very, very, very strong piece of evidence that supports the fact that the universe is expanding. So I would say it's one of the cornerstones of the Big Bang Theory is the fact that we know that the light from other galaxies is being redshifted. What we also know is that I guess no, but as a sort of an addition to it, the light that was emitted when the universe was half its size reaches the Earth with half of its initial energy. Basically, what this means is that when light was emitted when the universe was half of its size, the wavelengths of that light got doubled. So basically, the universe doubled in size, which means that wave got stretched as by a factor of 2. And so if the length of the wave increases by a factor of 2, the amount of energy it has is going to be reduced by a factor of 2. So longer wavelength is less energy. Shorter wavelength is more energy. So when the universe was half of its size, that light got stretched 2 times when it arrived to us now, which means the amount of energy it have is going to be half of what it used to be when the universe was half of its current size. Another important thing that we know is that the lights from the farthest objects are more and more redshifted. So the amount of redshift these galaxies, the light from these galaxies have, is not constant. Actually, the farther and farther away these galaxies are, the more and more redshifted the light is. So if we actually plot the data that we have from all these galaxies, we measured the amount of redshift these galaxies have, the light from these galaxies have, and we plotted it as a function of their distance. So on the x-axis, we have the redshift. On the y-axis here, we have the distance. So as you can tell here, the more redshift you have, the farther away these galaxies are. So stuff with low redshifts as 0.2, this is going to be much closer than here. So the farther away these galaxies are, the more redshift they have. And I want you to also notice how the relationship between the redshift and the distance is not linear. A linear relationship would look like this, like there's a one-to-one relationship. But as you notice here, it's actually an exponential relationship. So the farther and farther you get, the farther and farther you get, the faster and faster the amount of redshift you have is going to increase. It's like an exponential rate. The redshift is going to increase as an exponential rate with regards to the distance. So what this means is that not only is the universe expanding, it's actually expanding at an accelerating rate. So basically, the universe is getting bigger and bigger, faster and faster and faster and faster. So basically imagine if you're blowing a balloon. Initially, you're blowing the balloon very slowly, and then but then you start speeding up how quickly and quickly you're blowing up the balloon, and eventually the expansion rate of the universe will be so fast that it will exceed the speed of light, which basically means that at some point. So the thing is, the speed of light is the maximum speed of any object in the universe. Nothing can move faster than the speed of light. However, if the expansion rate is bigger than the speed of light, what this means is that we'll no longer be able to see some faraway galaxies. The light will just simply never reach us because the expansion rate is bigger than the speed of light. So I think we're fairly fortunate. Our universe is pretty young right now. 13.8 billion years doesn't seem young, but it's actually pretty young in the grand scheme of things. And which means that we can actually see pretty much, I think we can actually see, we're not at the point where we can't see stuff from other galaxies. However, in the future, what will end up happening is that some future civilizations, they will no longer be able to see light from these other galaxies. So they'll actually be sort of missing information. They just will, like, their laws of physics will be incomplete because they just simply won't be able to see these other galaxies. So we're actually sort of fortunate, or our understanding of physics has not been challenged by the fact that we can't see some galaxies. We're still fairly young. So yeah, so the redshift of these galaxies is increasing as you get further and further away, which means the universe is expanding, it's getting bigger, but it's expanding at an accelerating rate. So as the universe gets bigger and bigger and bigger and bigger, the universe also continued cooling, right? So as it gets bigger and bigger and bigger, the amount of space you have between particles also increases, which means it's going to get cooler as well. So eventually, it cooled enough that you could get the four following things were created: protons, which are positively charged elementary particles; neutrons, which are neutrally charged elementary particles; electrons, which are negatively charged elementary particles; and photons, which are massless particles of light. So when the universe was really, 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 really small and really hot, all these protons and neutrons and electrons, they are actually in their even more elementary forms, which we call quarks. Quarks are absolutely wild. I'm not qualified to teach you about quarks. But basically, if you think that protons are small, there actually are smaller things called quarks, and those are wild. And as far as if there's anything smaller than quarks, again, I can't really tell you. I'm not really an expert on that. But basically, it was too hot for protons and stuff to form. And as the universe continued cooling, eventually these protons, neutrons, electrons, and photons were able to form. Now, these protons and neutrons and electrons and photons, these in themselves cannot do anything at the moment. So if you learn chemistry, we have, different elements have different numbers of protons and neutrons and stuff like that. And they all have really cool things. Yeah, so none of that happened so far. Right now, there's just a sea of protons and neutrons, electrons and photons, but they can't do anything. And the photons in general really can't do anything because this universe is still too hot and too dense for anything to happen. Now, eventually, the universe did cool enough. As the universe continued expanding, it did cool enough to allow our first atoms to be created. Most of the protons combined with electrons to form hydrogen atoms. Some of the neutrons and protons were able to actually create helium and lithium. And this is a process we call nucleosynthesis. So the ratio of protons and neutrons heavily favored protons. There's a lot more protons than neutrons, which is why most protons form hydrogen, and there's a lot less of helium and lithium. Nothing heavier than lithium was able to be created. This is because the universe, in order to create elements heavier than lithium, it's a very lengthy process that requires a lot of very specific conditions. And the problem is the universe was expanding very quickly, and all this hydrogen and helium making in the Big Bang happened very rapidly. So there simply was not enough time to make heavier elements than lithium. So we were sort of limited to, and even honestly, there wasn't even that many. There wasn't even that much lithium either. It was mostly hydrogen, some helium, and tiny amount of lithium. And this is because the universe cooled it down enough to allow these to happen, to allow this to form. Okay, so what the universe continued to do, it continued getting cooler and cooler and cooler. The thing is, all these photons, before hydrogen was formed, all these photons could not do anything. They could not go anywhere. And this is because the density of the particles was simply too high. The universe was way too small, and there were way too many particles. It's basically like, imagine if you were on a really gridlocked freeway where the traffic was really bad, and you were trying to get from one end to the other end. Yeah, so you're not going anywhere because there's just so much just stuff blocking you. And basically that's exactly what happened with the photons. These photons wanted to go places, but the density of the cars or the particles around them was just too high. So none of these photons were able to escape. It was just way too high. As the universe continued cooling, eventually these photons and stuff were able to form hydrogen atoms. So when you create hydrogen atoms, you're basically taking some of these cars and you're basically combining them into bigger cars, and that basically frees up more space on the freeway. So now all these photons, they suddenly have a lot more space to work with. So all these protons and neutrons and stuff formed hydrogen really rapidly, which suddenly allowed all of these photons to just suddenly escape. So you have all this radiation. So in the Big Bang, in the early stages of the Big Bang, you have tons of energy. You got tons of these particles, and these particles suddenly formed hydrogen and helium and stuff. And suddenly now you have all this leftover energy, all this leftover radiation in the form of photons that suddenly can escape. So now they just escaped, and they just carried with them all the leftover energy and radiation from the Big Bang. And this happened almost all at once. It happened very quickly. So basically, for the first 380,000 years, no light escaped. And as soon as hydrogen was made, suddenly all this light escaped all at once. And that's what we call the cosmic microwave background. The cosmic microwave background is all these leftover radiation from the Big Bang that came all at once. Now, the cosmic microwave background itself was predicted by the Big Bang, right? The Big Bang predicted that the universe was originally very small and very dense, which meant that we would have had too high of a density for these photons to escape. And it predicted that as the universe continued expanding, that suddenly these photons would be able to escape once hydrogen atoms were made. So the Big Bang actually predicted the cosmic microwave background. So with this prediction, we actually set our telescopes to the sky, and we actually tried to look for this cosmic microwave background. And we actually did detect it. We actually did detect all of this radiation that the Big Bang predicted. So this was actually one of the most important verifications we have of the Big Bang, was the fact that the Big Bang predicted that we would see this cosmic microwave background of all this radiation that was suddenly able to escape. We predicted that, and we actually were able to confirm that. We actually confirmed that prediction with our telescopes and stuff. Now, one thing that I want to also talk about is the fact that the cosmic microwave background has the word microwave. So it has the word microwave for a reason. And this is because the radiation that we observed is all in the microwave spectrum. So originally, all this energy from the Big Bang was very, very high energy. So I don't know exactly what kind of light it was, but I'm assuming that it was probably like a lot of gamma rays, a lot of X-rays, a lot of very high energy. But if the universe, because the Big Bang theory predicted that the universe is expanding, what it also is going to predict is that these light waves are going to be stretched out as the universe is continuing to expand. So that means that all this radiation that was sent out, 13 billion years ago, all this light would have had 13 billion years to basically have all of its wavelength stretched out. So during the course of these 13 billion years, all this light is just continuously being redshifted and redshifted and redshifted. So if it originally was very high energy, by the time it reaches us, all this radiation is now very low energy. So basically, there was so much redshift that we went from being high energy to being low energy microwaves. So the Big Bang, right, predicted that, and we actually were able to predict that, okay, that when we look at this cosmic background, if we were to search for it, we would predict that the radiation would be in the microwave spectrum because of how much the universe would have had to expand by then. So we actually predicted that the radiation should be in the microwave spectrum. And so when we looked sent our telescopes to the sky and looked at it, we actually did find it in the microwave spectrum. So this is a very also one of the key pieces of evidence that supports the Big Bang Theory. Very important to know. And it's also going to be very important to be able to connect this piece of evidence and use this to describe, support why the Big Bang, to support how does this support the Big Bang? How does the Big Bang predict this? So what we're going to do now is I'm going to put you in your groups and I want you to try to think about how does the existence of the cosmic microwave background support the Big Bang Theory? So, in other words, how does the existence of the cosmic microwave background suggest that the universe is expanding and that it originally came from a much smaller, much hotter, and denser point? You're going to want to think about whether or not the CMB could exist in the early stages of the universe. So try to connect the evidence and use the evidence to try to explain / support the Big Bang Theory, and then see if you can connect the evidence to the Big Bang Theory. So I'm going to put you in your groups now, and then we'll take some time to try to figure out how does the cosmic microwave background support the Big Bang Theory. Okay, so let's talk about the cosmic microwave background because this is kind of a tough topic. So how does the CMB support the Big Bang Theory? So first off, what is this cosmic microwave background? Well, the cosmic microwave background is basically a ton of radiation that occurred all at once that carried all this leftover energy from the Big Bang. And what I want to reiterate is the fact that it occurred all at once. So it's not like, this occurred over, all this radiation was being exposed over 13 billion. No, no, no. It literally occurred like very quickly, all at once. And nothing happened before all this CMB. So there was no radiation from before this. So why did all this radiation come all at once? Well, the only way this radiation could have came all at once is if these photons were sort of being bottled up, if they were sort of being locked around and they weren't able to move. So basically, like imagine if you had a bunch of first graders in a classroom and they were trapped there, and then you open the door and then you said recess, right? Then all these first graders are going to come running out, and then they're going to be, taking over the world. So that's basically the same idea. You're basically, the only way to have all this radiation come at once is if all these photons were being bottled up. So what could have bottled up these photons from doing that in the first place? Well, what that must have meant is that the universe had to have been a lot hotter and a lot denser in the past. So that way, because hydrogen atoms allow photons to pass through them. So the universe must have been so hot that hydrogen atoms were not able to be formed yet. So the universe at some point must have been much hotter and much denser and much smaller, so that you only had protons and neutrons and electrons and not hydrogen yet. So that basically what the CMB tells us that, okay, the existence of all this radiation tells us that back in the day, the universe had to be much smaller and much hotter and much denser because the only way CMB the radiation could have escaped is if there wasn't any hydrogen atoms yet. So the universe had to have expanded from this small point to an area that's big enough and cool enough for these hydrogen atoms to form. Now, on the flip side, another thing you also want to think about is the fact that the CMB is the microwave background, the microwave being in the microwave spectrum. So the radiation that emitted from this, that was originally left over from the Big Bang, it must have been very high energy, right? The Big Bang was very high energy. So the radiation should have been very high energy as well. But when we observe them in the microwave spectrum, which is very low energy. So what could have happened from over the 13 billion years to have all this energy, all the CMB lose its energy so much that it actually ended up as microwaves. So this is what we call the process of redshifting, right? Redshifting is the fact that all this energy is the fact that all these light is losing its energy over time. So there must have been 13 billion years of redshifting for all this energy all the radiation from the CMB to lose so much energy to become microwaves. So what that must have meant is that from the time that the CMB was emitted, the universe had to have been continuously expanding and getting bigger as a way of redshifting the light more and more and more. So eventually, when it came to us, it was all in the microwave spectrum. So all in all, the CMB in itself already tells us that the universe had to have been very small and very hot and very dense, and that it expanded enough to release the CMB, and then it continued expanding to the state that it is now. So basically, this whole idea that it was very small and it's been expanding this whole time. So the cosmic microwave background is probably the second big piece of evidence that we have. The third piece of evidence we have relates to something called nucleosynthesis, which is the formation of atoms larger than hydrogen. So the nucleosynthesis, the process of nucleosynthesis, once again, the formation of atoms larger than hydrogen. On the Big Bang Theory nucleosynthesis, the theory itself predicted that there would be a ratio of 1 neutron to 7 protons, which if you do the math, it actually predicts the universe will be roughly 75% hydrogen and 25% helium. The reason being that hydrogen has protons, but no neutrons, and helium needs neutrons and protons. So because there's many more protons than neutrons, right, you can't make that much helium. So most of it will actually be made into hydrogen. So based on the math, the universe will be roughly 75% hydrogen and 25% helium. So this is what the Big Bang Theory predicts. This is the evidence that we have in person. So using our telescopes, we were actually able to observe what the composition of stars and interstellar gases are in other galaxies. This is what the evidence we have states. Based on our data, we found out that stars and interstellar gases are in general composed of about 73% hydrogen, 25% helium, 2% lithium, and 0% other. And this is that temperatures and the density were too low in the Big Bang to form heavier elements. So this is the evidence we have. We found that it's roughly 73% hydrogen, 25% helium, 2% lithium, and then 0% other. So does the astronomical evidence we have support the support? Does the astronomical evidence about the composition of stars and gases, does that support the Big Bang Theory? Why or why not? So I'm gonna give you a few minutes to try to come up with your ideas. Do you think the astronomical evidence supports the Big Bang? Why or why not? Let's take 1 more minute. And I'm gonna do a quick recap of the Big Bang. Okay, so now to quickly recap what the Big Bang Theory is and the chronology of events. Basically, in the very beginning, the universe started as an infinitely small and extremely hot singularity. Everything was condensed into this tiny, 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 tiny point. And so it's very, very, very hot. The universe then began expanding very rapidly. And this is through the process called inflation. And inflating a balloon, that's what the universe was doing. It was basically inflating. And we actually know this from evidence that the light from the galaxies are redshifted. So basically, we knew what the light from galaxies should look like. And when we compared that to what they actually look like, we noticed that the light from the galaxies were all of lower energy than what they should have been. This is what we call redshift. Redshift is when the light has lost energy on its way here. So when we realized that, okay, the only way these galaxies could have lost, the light from these galaxies could have lost energy is that the galaxies were getting farther away from us, which could happen if the universe was expanding. And not only is the universe expanding, it's actually expanding at an accelerating rate. So it's getting bigger and bigger, faster and faster and faster. So as the universe continued expanding, it then kept cooling very rapidly. So within the first few minutes, eventually cooled enough where we could form protons, electrons, neutrons, and photons. Before then, it was too hot to form any of these. They were all just a sea of quarks and stuff. Eventually, eventually it cooled down even more so that some of these protons could combine with electrons to form hydrogen atoms. Well, first it's hydrogen nuclei, but hydrogen atoms essentially. When all of these hydrogen atoms were being formed, the photons that were previously just locked in, that couldn't move because they were being trapped by all these protons, electrons, and neutrons, because these hydrogen atoms were being formed, all these photons had a lot more room to move. And so as soon as these hydrogen atoms started forming, all these photons suddenly were able to travel freely through the universe. And all these photons carried with them the leftover radiation from the Big Bang. And this is what we call the cosmic microwave background. Basically, all this leftover radiation from the Big Bang was suddenly able to escape and travel freely through the universe. Now, not all of these protons formed hydrogen. Some of these protons combined with the neutrons to form helium and lithium. And this is through a process which we call nucleosynthesis. The Big Bang Theory itself predicted that the mass of the universe should be roughly 75% hydrogen and 25% helium. And when we actually not measured, but when we actually observed what the composition of stars and gases are in the universe, that actually confirmed what the theory predicted. However, in the Big Bang, we couldn't form additional elements because the fusion process in the Big Bang Theory was very short. So any other elements heavier than lithium, like carbon, oxygen, whatever, those were not formed during the Big Bang. Those were actually formed in stars, which we'll talk about, but they were not formed in the Big Bang. So the Big Bang only explains how hydrogen and helium and lithium were created. So that is pretty much the Big Bang in a very quick 1 hour summary. And so that's pretty much going to be it for today. Hopefully you guys learned something. And then we will continue talking about stars and universes on Friday. So other than that, I will see you guys then.
Thank you.
Thank you.
Bye. Bye-bye.
Thank you.
Thank you, Mr. Hu.